Good evening, all. Am I audible?
Yes, ma'am.
Okay. So, how many of you are having the Python OPP exam tomorrow?
I have, ma'am.
I have.
Okay. So, all prepared for it?
Need to practice.
Okay. Okay. Anyway, this again, I'm repeating. Tomorrow there won't be a live session. So you can do your preparation for Python and do the exam well. So Monday, Tuesday, the mock for quiz 2 will be released, and means it will be open for attempting for those 2 days. So you can attempt on Monday and Tuesday. Today we will try to cover most of week 8 content. We should be able to cover at least 80% of it. If we are not able to complete it fully, then in Tuesday's session it will be completed, and you can attempt the mock with that also. Like, yeah, whatever is needed mostly will be covered today, at least the definitions and all that I'll tell. You can try it out on your own. Anyway, in Tuesday's session, we'll continue week 8. Okay.
Okay.
Yeah. So, in the last session, we were discussing about inner products and all that, right? So what is an inner product? What is an inner product space? Can you quickly tell me what an inner product is?
Dot product of each and every element within that element.
No, the dot product is one of the inner products, but the inner product is something more general. It is a function from a vector space to real numbers, satisfying certain conditions, satisfying 4 conditions. The first condition is the positivity condition. We want inner product of a vector with itself to always be non-negative and equal to 0 if and only if the vector is equal to 0. So this is the first condition. This is positivity, and then we had linearity with respect to the first variable. So v1 plus v2 comma v3. When we take inner product of v1 plus v2 with v3, that should be equal to inner product v1 v3 plus v2 v3. This is for all v1, v2, v3 in the vector space. And then the scalar thing. So when I multiply the first component with a scalar, alpha v1 comma v2 should be equal to alpha times inner product v1 with v. And alpha is any real number. And the last condition is symmetry. v1 v2 is equal to v2 v1. Inner product of v1 v2 is equal to inner product of v2 v1. So if these 4 conditions are satisfied, then we say that this function is an inner product on the vector space V. Yeah. And V along with this function is said to be an inner product space, right? So if an inner product is defined on the vector space V with that function, the inner product that is defined, is said to be an inner product space. Okay. Then what was norm of a vector? How did we find norm using the inner product?
Length of that vector.
That is length of vectors which is the
norm of any vector is square root of inner product x with itself. So this inner product is based on what the definition of the inner product is, not the usual dot product always, right?
Yes.
Yeah. So you have to be very careful with respect to that. When you're calculating the norm of a vector, you should calculate it with respect to the inner product that is given, not the dot product always. So yeah, and norm is a function satisfying 3 conditions and all that. Okay, fine. So all this was discussed previously. Now on inner product spaces, what and all can we see? So yeah, that's what week 8 is all about. So yeah, orthogonal vectors. When do you say two vectors are orthogonal? In R2 only. Let's talk about R2. When do you say two vectors are orthogonal?
If the dot product is 0.
Yeah, if the dot product is 0. So if the dot product is 0, what happens to the angle between those two vectors?
90 degrees.
90 degree.
90
Yeah.
because 90 is 0.
Yeah. So since the dot product is 0, the angle between those two vectors is actually 90 degree. So any two perpendicular vectors are orthogonal vectors, right? Yeah. So that's what we call to be orthogonal. So the basic concept is that the dot product of those two vectors is 0. So generalizing this, we talk about orthogonal vectors. So two vectors are said to be orthogonal if the inner product of those two vectors is 0. And this inner product will be based on the inner product that is defined. So V comma this function is an inner product space. So whenever we talk about an inner product on this space, we will always consider the inner product that is defined on V, not the dot product always. Okay, so you need to be really careful when you're dealing with inner products. You should check for how the inner product is defined. So two vectors are said to be orthogonal if the inner product of those two vectors is 0. That's all. As simple as that. And when do you say a set of vectors is orthonormal?
And norm is 1.
Along with the orthogonal.
Yes, orthogonal.
Yeah. Orthonormal means orthogonal and
the norm
unit
of that
vector.
vector.
Unit vectors means norm is 1, right?
Yes.
Yeah. So if these two are satisfied, then you say that the set of vectors is orthonormal. That's all. So this is the basic thing that we'll be seeing in week 8. So two non-zero vectors are said to be orthogonal if inner product u comma v is equal to 0. And a set of vectors is orthogonal if every pair of vectors is orthogonal. So if you have a set v1, v2, etc., vn, then every pair v1, v2, v1, v3, v1, vn, like that every pair of vectors should be orthogonal. If that happens, then you say the set is an orthogonal set. And this one. If I have a set of orthogonal vectors, let v1, v2, vn be a set of orthogonal vectors, then this point says that it is linearly independent. Can you think of how this is possible? I have a set of orthogonal vectors. What it says is that it is linearly independent. So I have an orthogonal set implies it is a linearly independent set. How is this possible?
When all the solution is unique.
Yeah, you should take
between them is 90.
Okay, but we cannot talk about angle in general in a product space. Okay, fine. Let's talk about Rn only, R2 only. So, okay, if they are if the angle is 90 degree, why should they be linearly independent? Only one solution.
The other component is 0.
Okay, if I have two vectors, let's talk about a set.
They are going in different directions, ma'am. So they'll not. I mean, I'm not able to completely frame it, but I understand because they are perpendicular. Right.
Yeah. If they are linearly dependent, then they should have been in the same parallel direction, right? Like they should be scalar multiples of each other. Yeah. So that's not happening. So yeah, that's one way of seeing. So if I have a set of two vectors, this is fine. What if I had a third vector? Can three vectors be orthogonal in R2?
No. No. The third set will be the third vector will be linearly dependent.
Yeah, because if it is an orthogonal set, it has to be a linearly independent set by what I just said. And 3 vectors cannot be linearly independent in R2, right? The maximum number of linearly
2.
independent vectors is 2. Yeah.
Can it be
So let's
vice
prove
versa?
this. No. I'll give you an example. Yeah. So if I have a set with 2 vectors, so you can, if I have more than 2 vectors also, I can do the same proof, just that you have to take every pair of 2 vectors. That's it. So if I have a set with 2 vectors, it is orthogonal. I'm assuming it is orthogonal. I want to prove it is linearly independent. To prove this set is linearly independent, what should I do?
Every scalar's multiplication is 0.
Linear combination will be 0.
Yeah, linear combination will be 0. Alpha 1 V1 plus alpha 2 V2 is equal to 0 implies alpha 1 alpha 2 is equal to 0. I want to show that the coefficients are both 0, right?
Yes.
This is what I want to show. This is to prove. This is given. Okay. So now what do I do? I have alpha 1 V1 plus alpha 2 V2 is equal to 0. I want to show alpha 1 is 0, alpha 2 is 0. How are we going to do that? It's given this is an orthogonal set. So make use of that. If it is an orthogonal set, what do we know?
Dot product is 0.
Dot product is 0.
Not dot product, we'll say inner product, okay? Because if you say dot product, you'll get used to the dot product concept. Instead, say inner product. So inner product is 0. Okay, how can we use that here?
You can take this is a B1 or alpha or anything else B.
Okay, and
we can perform dot product. So when you take that is a B, so you can take orthogonal of B comma B, that will be equals to 0.
so which one is V? You're telling take this to be V, is it?
Yes.
Okay, and then what are you telling? Take inner product of V with?
V1. V1, madam.
B with B.
V with V1.
Yes.
What is inner product of V with V1?
V alpha 1. Alpha 1 V1 plus alpha 2 V2 V1, then alpha V1. Yeah.
So I can do that linearity thing, right?
Yeah.
Yeah. So I can write this as alpha 1 V1 with V1 plus alpha 2 V2 with V1.
Yeah.
What do I know about V2 with V1? Inner product of V2 with V1?
0.
Yeah.
Because orthogonal.
So this is 0. And what do I know about this?
0.
This is 0, right? Because I've assumed that this is equal to 0.
Independent.
No, I want to show it is linearly independent. So I've assumed this is 0. So what is inner product of 0 with V1?
0.
Yeah, inner product of a vector with the 0 vector is always 0. So I have 0 is equal to alpha 1 V1 with V1. Yeah. So, okay, obviously we assume V1 and V2 are non-zero, right? Otherwise this linearly independent doesn't make sense, right?
Yes.
Yeah. So what if V1 is non-zero, what can I tell about inner product V1 with V1?
Alpha 1 equal to 0.
Alpha 1.
Why this is not equal to 0?
Because V1 is non-zero and
non-zero vector is
zero vector.
Yeah. So we have that condition, right? The inner product is equal to 0. V with V is equal to 0 if and only if V is 0. Yeah.
0.
So because V1 is non-zero, the inner product has to be non-zero. So this forces alpha 1 to be equal to 0.
Ma'am, can you explain again?
Yeah. Okay. So I'm given a orthogonal set, okay? And I want to prove that the set is linearly independent. So instead of taking v1, v2, vn, I'm just taking for two vectors, v1, v2. Suppose the set has two vectors, v1, v2. I'm assuming that the set is orthogonal, which means that the inner product of those two vectors is equal to 0. Inner product of v1 with v2 is equal to 0. I want to prove that the set is linearly independent. What should I do for that?
Then after I confuse what you do in this whole.
So if I want to show something is linearly independent, how do I do that? You'll take the linear combination equal to 0, and then you want to show that the coefficients are 0, right?
Yes.
Yeah. So this is earlier week's content. Means the definition of linear independence. So now you see why we say quiz 1 portion is weeks 1 to 8. Because everything needs to be used. Otherwise, you cannot just rely on weeks 5 to 8 and pass the quiz. Everything is interrelated. That is why the portion is 1 to 8. Okay, fine. So to show that the set is linearly independent, I should take a linear combination equal to 0 and then show that the coefficients of these vectors are equal to 0, right?
Yes.
Yeah. So this is what I want to prove. Okay. So now I have to somehow relate this with the inner product stuff. So what I'm doing is I'm taking inner product alpha 1 v1 plus alpha 2 v2 with v1. What is this vector alpha 1 v1 plus alpha 2 v2?
It is linear orthogonal.
That is 0.
It is 0, right? I have assumed that. I want to show alpha 1 and alpha 2 are equal to 0, right? Yeah, so let me write that also. Suppose alpha 1 v1 plus alpha 2 v2 is equal to 0. I want to prove alpha 1 and alpha 2 are 0. Okay. So this is alpha 1 v1 plus alpha 2 v2 comma v1 I want to do. What is this?
V
will be 0.
Yeah. So what is the inner product of 0 with v1?
0.
Yeah, it's 0. Now if I expand this inner product, what do I get? Using linearity of inner product. Can I write this as alpha 1 v1 comma v1 plus alpha 2 v2 comma v1?
Yeah.
And then I can take the alpha 1 outside, right? v1 v1 plus alpha 2 v2 v1, right?
Yes.
I already know this v1 v2 is an orthogonal set. So inner product v1 v2 is 0, right?
Yes.
So this term is 0.
Yes.
So now I have 0 is equal to alpha 1 v1 with v1. Can I say this implies alpha 1 is equal to 0? Can we say this?
Yes, ma'am.
Yes.
Yeah. This is because v1 is not equal to 0. And if v1 is not equal to 0, then inner product v1 with v1 is also not equal to 0. Because of that, I can say alpha 1 is 0.
Excuse me, ma'am.
Yeah.
In order to prove alpha 1 equal to 0, we want to take the inner product of v comma v1, isn't it, ma'am?
Yeah. Yeah.
Correct. Okay.
Yeah.
If you
So
want to
this is
take
the
alpha 2, then we need to with the v2.
Yeah, exactly. So yeah, that's what my next question was going to be. So if I want to show alpha 2 is 0, I do the same procedure, right? With v2, alpha 1 v1 plus alpha 2 v2 comma v2 is equal to 0. I use this and then show alpha 2 is 0, right?
Yes, sir.
Yeah, I repeat the same procedure. Instead of V1, if I take V2, this term will be gone. The first term will be gone and the second term will survive. From there, we'll get alpha 2 is equal to 0. So are we done? Have we proved
Yes.
what we wanted to prove?
Yes, ma'am. Clear.
Yeah. So every orthogonal set containing non-zero vectors is linearly independent. Okay. So someone had asked about the converse. Is every linearly independent set orthogonal? Is it true or false?
It is false, madam. It is not always possible.
Yeah. Can you give an example?
Example.
Example was
If I want,
in
Like
the
if I want
example
to
was
show
given
something
in
is
the
true. Yeah, go ahead. Please go ahead.
example was given in the course material. It was orthogonal but not linearly independent. There was an example.
No. If
1001.
it is orthogonal, then it will always be linearly independent. The
Linearly
other way is
independent.
1001 for R2.
One.
no 1001 is an orthogonal set, right?
Yes.
Yes. That is a
1 1 1 1 2 0.
1 1 1 1 1 1 minus 1.
Okay, fine. Let's talk geometrically. What do you want? You want a linearly independent set which is not orthogonal. Orthogonal means they have to be at 90-degree angle, right? In R2.
Yes, madam.
And if it is linearly independent, it means they are not scalar multiples of each other, right?
Yeah.
Yeah. So you can always find two vectors at an angle of 30-degree or 60-degree or
45
anything.
degree.
Right?
Yeah.
Yeah, anything. Yeah.
Okay.
So you can just take 1 1 1 0 as someone
Yeah.
said. This
So
is the
this is-
linearly independent set.
But,
But
not
when you
all.
take the inner product, yeah. In R2 comes with, means when we talk about R2, when we talk about this angle cos theta, we are talking actually about the dot product, right? Not any other inner product. When we talk about angles in R2, we are talking about the dot product. So R2 with the dot product is an inner product space. And with respect to dot product, these two vectors are not orthogonal, right? The dot product is equal to 1. So it is not orthogonal, but this is a linearly independent set. So the converse is not true. To show something is true, you have to write a proof. To show something is false, it is enough if you give one example that does not satisfy whatever you want to show. So here we are giving an example. Is it clear?
Clear, ma'am.
Okay. So maybe we'll quickly do some problems and proceed. So here you're given a set of vectors 1, 2, 3, 4, 5, 6, 7 from the inner product space R3 with usual inner product, that is the dot product. Now, first of all, tell me, can S be orthogonal? Can the set S be orthogonal?
No,
Why not?
No.
because there are more than
That
3
has
vectors.
more than
Vectors.
Yeah. So if S was orthogonal, it would have been linearly independent.
Independent.
S is a subset of R3. So the maximum number of elements it can have is 3.
3.
But then it has 7 elements. So obviously S is not orthogonal. Okay. Which of the following subsets of the set S consist of mutually orthogonal vectors? Now, how do we check whether it is mutually orthogonal?
Pair
Inner
wise.
Yeah.
Pair
Pairwise
wise.
you take, yeah. Here the inner product is the dot product. So you just need to do dot product. Option 4 has been ruled out. S is not. So yeah, that's out. Option 1, is it
Is not.
orthogonal?
Option 2 is.
Option 1, you can take the first vector and the second vector. The dot product is 1 into 1 minus 1 into 2 minus 1 into 0. So that's what? Minus 1. That's not equal to 0. So this set is not orthogonal. Option 2.
Is. It is, ma'am. It is
1 into minus 1 minus 1 into half minus 1 into minus 3 by 2. So this is minus 1 minus half, yeah, plus 3 by 2. So yes, it is orthogonal. Option 3, we already know these two vectors are orthogonal. Okay, so it's enough if we check with the third vector. 1 times 1 minus 1 times 2 minus 1 times 0. It's not, right?
It is.
1 minus 1 minus 1 into 1 to 0.
No,
1.
it's
It's
No.
not, right?
It's
not.
not. Yes.
It's not.
Okay. Option 5. 2 minus 1 minus 1.
Yeah, ma'am, it is.
It is.
Okay.
Yes. It
Fine.
is.
So this is orthogonal. So option 2 and option 5 are correct. Okay. We missed out this basis thing. So when do you say what is an orthogonal basis?
Maximal orthogonal vector.
Yeah, a basis which is also an orthogonal set. That's it. A basis, you know what a basis is. You want all the elements of the basis to be orthogonal to each other. That is, inner product of any two elements in the basis should be equal to 0. That's all. That is an orthogonal basis. Or in other words, you can tell a maximal orthogonal set is an orthogonal basis. If it is maximal orthogonal, what does it mean to say it is maximal orthogonal?
It is not possible to add another vector to be as independent.
Yeah. So if you add another vector to that set, then the set loses its orthogonality. Then you say it's maximal orthogonal. If it is maximal orthogonal, it will be maximal linearly independent. So it will be a basis. Okay, fine. What is an orthonormal set? As already told, it is an orthogonal set where every vector is a unit vector. The norm of every vector is 1. Yeah, and you have the concept of an orthonormal basis. Again, it is a basis which is also an orthonormal set. Okay, if I have an orthogonal set, can I convert it into an orthonormal set?
Yeah, ma'am.
How will you do that?
Dividing by
Norm value.
Yeah, that's all. So you already have an orthogonal set, means the vectors are perpendicular to each other, or the inner product is 0. So to convert it into an orthonormal set, they are already perpendicular, means they are already orthogonal. You just want to convert them into unit vectors. That you can do by dividing by the norm. So you divide by the norm of each vector. And when you divide by the norm, you're getting a unit vector, right? What is the norm of V1 by norm V1?
1.
Yeah. Why is it equal to 1?
Because norm V1 by norm V1 is equal to 1.
So when you have
norm, yeah.
When you have alpha norm of alpha V, what you do is mod alpha times norm V.
Norm
the
V,
property of norm. So here 1 by norm V1 is a scalar. You take that out into norm V1. So this is 1. So any vector, when you divide by its norm, it becomes a unit vector. So if you have an orthogonal set, you just divide every vector by its norm, you get an orthonormal set. Okay.
Ma'am, it is also linearly independent or not?
Yeah. If it is an orthonormal set, it is like the heart of it is orthogonal. Yeah, it is actually orthogonal. In addition to that, you have some property. So if it is orthogonal, it is linearly independent, right? See, here if it was orthonormal, this would have been 1, right?
Yes.
Yeah, but if it is orthogonal, it can be any other number also. That's all.
Ma'am, can you, quick question, sorry. Can you tell me how do you calculate the dot product between, say, two vectors, 1 minus 1 minus 1 and 1 to 0? I missed that part. I apologize.
No problem. So here it's dot product, right? So you have to multiply each component. How is dot product defined? x1, y1, x2, y2 is defined as component wise multiplication and then addition. x1 into x2 plus y1 into y2. So here it will be 1 into 1 plus minus 1 into 2 plus minus 1 into 0.
0. Okay.
Thanks, so
Thank you.
1, yeah, minus 1. Yeah.
Ma'am,
Yeah.
what your meaning inner product space R3? Inner
product.
Space
Inner
R3.
product space means R3 is a vector space, right?
Okay. So
you agree that R3 is a vector space, right?
Yeah.
And you can define an inner product on R3, right? You already know the inner product, dot product.
Okay, inner product on R3. Okay.
Yeah. So then you say it is an inner product space. That's what I had written here. Okay. So you have an inner product on the vector space V. So V along with that inner product is called an inner product.
Okay, madam.
Yeah. Any vector space on which you can define an inner product is called an inner product space. Okay. So continuing, we have that set S which has 7 elements and all that. Okay, fine. So here now we have certain options. This is related to orthogonal basis and orthonormal basis. Okay, fine. So first of all, this one 2, 1, 1, 0, 1, minus 1 is an orthogonal basis of a vector space which is isomorphic to R2. A lot of concepts are involved here. First, tell me what is an orthogonal basis. Before that, what is a basis?
If inner product is
zero.
No. Basis. What is
it? It is the minimum, minimal,
maximal vectors.
Minimum number of vectors which is required to define a vector space.
Yeah.
Cardinality of basis is equal to cardinality of basis is equal to dimension of
orthogonal
R square.
Maximal linear spanning linear independence.
Yeah, a lot of definitions of basis you have told, and most of it is correct. So it is either a maximal linearly independent set or a
minimal spanning set.
So this is a basis is a set which is like you add any vector to it, then it loses its linear independence. So that is the maximum number of vectors which can be linearly independent in that space. And it is a minimal spanning set means it is the minimum, it contains the minimum number of vectors such that those vectors span the entire vector space. That is a basis. And the number of elements in any two bases is the same, and that is called the dimension of the vector space. So all this is already known to you. So when do we check a basis is orthogonal or not? What is an orthogonal basis?
Inner product is zero.
Yeah. So it is a basis first of all, and on top of that, the set is orthogonal. Okay. So if there is no, okay, already it is mentioned, no, dot product is already mentioned. Okay. If nothing is mentioned, you take the dot product, but we will make sure that we mention it everywhere. Okay. So what is the dot product of these two vectors?
Zero.
Okay. So this is an orthogonal set. So the question is it an orthogonal basis of a vector space which is isomorphic to R2? What is isomorphic? What is an isomorphism?
It is a
both surjective,
at the same time bijective and surjective.
Means it is bijective.
It is bijective.
Yeah, bijective.
A linear transformation which is bijective. That's all. 1, 1 and on 2. Perfect. So now what are we interested in? We have a orthogonal set. Can this set be a basis for some vector space? Yeah. What is the vector space?
So it should be R2, right? R2 vector space, right?
2x.
No.
2x.
R2. R2 has only 2 components, x comma y. Here I have 3 components. But the question is, can this be a basis for any vector space?
Yeah.
Yes.
Yes,
2x plus x plus y, x comma x minus y.
Okay. So yeah, you're almost there. But yeah. So the space is span of that set, right?
Yes, ma'am.
That's what you said, but maybe if we write it down, yeah, we'll get x times this plus y times this and all that. Okay, fine. So for this vector space, this set in option 1 is a basis, right? Because we know it's already linearly independent. It is an orthogonal set, so it is linearly independent. Now, if I take the span of those two vectors, for this vector space, this is a basis, right?
Yes.
Yeah. So this is a subspace of R3, right?
Yes, ma'am.
Yes, madam. Yes, madam.
So now we are interested in finding whether this is isomorphic to R2. So can I define, is there a T? Is there a T from
R3 to R.
R3 to R2.
Yeah.
Not R3, W.
W
We are
to R.
talking about the vector space.
Yes,
W
ma'am.
to R2 such
Subspace.
that T is an isomorphism.
Why W is not R3?
No,
Because it is a
W is
subset of R3.
two-dimensional, no?
Okay.
It has only 2 elements in the basis. It is given that this is a basis of a vector space. That vector space for us is W. Means in our notation, we have taken it as W.
So me,
Okay.
ma'am, subspace is called subset. Is it equal, na? Subspace or subset?
No, subset means it's just a set. Subspace means it is a subset which is also a vector space.
Okay.
Yeah.
Set,
So this
which
2,
is
1, 1,
No.
this is a subset. This is a subset. But W is a subspace. This is a subspace. Yeah.
only single vector is a subset.
So W is
This is
subspace.
a subset.
So, madam, W is subspace of R3, na, madam? W.
Yeah.
Yeah, that's why I am saying. Subspace. Yeah.
Can you define an isomorphism from W to R2?
No.
Yes, ma'am.
Because
How?
N is
Because
N is greater than M type
nullity,
condition we can use.
if we can
No,
use,
no, no.
ma'am,
Cannot
No.
be
rank nullity theorem,
Okay.
then nullity is 0, because
Okay.
since both are linearly independent, so 0 can be written as the linear combination of this, and only possible way is when A and B are 0. So nullity
Okay,
will
fine.
be 0. Nullity will
But
be
nullity
0.
of what? We haven't
Null-
even defined the transformation, no?
Ma'am, we are defining here, na? There is a transformation from W to
No, is
RX
there a
square.
transformation?
Is there? But if we assume that there is, then we
If
can
there
say
is,
that.
then fine. Okay.
Yes, ma'am.
But the
Then,
question is, can I define an isomorphism?
Can't we check, like, ma'am,
if
considering
nullity
like
is 0, if nullity is 0, ma'am, then it's 1 1, and dimension of V is equal to dimension of this range, that is rank. So it's on to 2. So there is isomorphism.
Yeah, fine. But my question is, how will you get that transformation whose nullity is 0? So you have to basically define T of some x comma y comma z is equal to something comma something, right? Where
Yes.
this x comma y comma z belongs to W.
Yeah.
How are you going to define that?
You can write linear combination of those two vectors.
Okay.
First, we have to find W, madam. Like x, y, z is equal to alpha into 2, 1, 1 plus beta into 0, 1, minus 1. Then
That
we
will
find
give
alpha and beta and put the
Yes, ma'am.
value of alpha and beta, and then t x y z is equal to something like that.
Okay, fine, perfect. So your way of finding a linear transformation given a basis is perfect. But is it necessary to find out this x, y, z? Do you know that if we define the linear transformation on the basis, then I know the linear transformation on the subspace?
Yeah, like we can take transformation of 2, 1, 1 as 1, 0 and other as 0, 1 or something like that.
Perfect, that's all. So you just need to fix the images of these two basis vectors, right? Then the transformation is fixed, right?
Yes.
Yeah.
Ma'am,
So
can
you
you show
just
me?
Ma'am, without finding this, we cannot say that
without finding what?
This
T of
ma'am,
2, 1,
this
1 equals to 1, 0.
No, but the question is, there is an isomorphic. Okay, this is an orthogonal basis of a vector space which is isomorphic to R2. To show that this subspace is isomorphic to R2, you have to define an isomorphism, right? Only if there is an isomorphism, these two are isomorphic. So you need to find a T such that this is an isomorphism.
Okay.
We need to assume that.
So you could have defined a T of 2, 1, 1 to be 0, 0. T of 0, 1 minus 1 to be 0, 1. Is this 1 to 1?
No.
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 Why is it not 1 to 1?
Because any here in case you took 2, 1, 1, so any
0, 0.
we can take 4 to 2 also will tend to go to 0.
Find 0,
2, 1, 1 belongs to the kernel, right?
yes.
So nullity will not be 0. But for an isomorphism, I want nullity to be 0, right? So first of all, I should make sure that none of the basis vectors go to 0. Right?
Yes.
And you also want range to be R2. Correct? Only then rank will be equal to 2. So if the range has to be R2, you just take a basis for R2 and put it on the right side, right? Because I had told you, no, TV1, TV2 is a basis for range. If V1, V2 is the basis for domain. This implies TV1, TV2 is a basis for range. And I want the range. Can you please mute if you're not talking to me?
So here the transformation matrix will be nothing but 1, 0 and 0, 1, right?
No, the transformation matrix means, no, what is
If we
transformation
expand it,
matrix?
so like since 2, 1, 1 is getting converted into 1, 0, this is nothing but 1 into 1, 0 plus considering the basis of R2 to be 1, 0 and 0, 1.
Yeah, so there you have to do that, X, Y, Z in terms of all that.
Got it. Yeah, and just substitute back and okay, got it, ma'am. Yeah. Yeah. Thank you.
So it's not necessary that it should be 1, 0, 0, 1. You can,
yeah, I mean, this is one of the case, right? To prove that the linear transformation is possible. Like,
yeah. So yeah, whoever was talking, you can unmute and talk.
yeah. So in order to, so here in this case, it is like, it's just enough to show this, right? Like transformation of 2, 1, 1 is 1, 0. So this basically means that any two-dimensional vector space is isomorphic to any R2 plane. And similarly, any three-dimensional vector space is isomorphic to any R3.
Yes.
Orthogonal basis vectors again.
No, it's not necessarily orthogonal.
Yeah,
No?
just got it. Yeah, it can span the whole space. So yeah, got it, ma'am. Thank you.
Yeah. So any line will be any line in R2, any line passing through the origin, obviously, any subspace, that line passing through the origin is going to be isomorphic to R, the real line. And any plane in R3 is going to be isomorphic to R2, and any line passing through the origin in R3 is going to be isomorphic to R. So like that, we can talk about.
It's basically linking from same dimension to same dimension. If it is,
exactly.
If the basis is defined from 2 dimension to R2 or 2 dimension to 2 dimension, it will always be isomorphic.
No, not necessarily. It will always be isomorphic, but you can define an isomorphism. Means.
Yeah. Yes.
Okay. Yeah.
If there is a transformation between that to this, then it will be isomorphism. Because there can only be a single 0 and everything else is 1, 1. To define everything. Yes. Thank you.
So basically, any two vector spaces of the same dimension are isomorphic.
But
you can think
here,
of.
ma'am. But ma'am, here codomain have 3 dimensions, ma'am. 2, 1, 1. Like
No.
What is it? Dimension.
W is the subspace of R3, but what is the dimension of W?
Dimension of W less than equal to R3.
Okay, fine. No, but we exactly know a basis. No, this is a basis for W.
Oh, basis is 2. Okay, so dimension is 2.
Yeah, and R2's dimension is also 2. So I can define an isomorphism.
Isomorphic. Okay, madam. Now it is.
Yeah. Okay. What about option 2? Is not an orthogonal basis of a vector space which is isomorphic to R.
It is a orthogonal basis, I guess, since it's a single vector.
It is, right? It is a isomorphic. Like just like how we did for R2, means R2 here for option 1, we can do it for R, right? Because it's just one vector here. So it is obviously linearly independent. Take the span of that. You're going to get a line passing through the origin, and that's going to be isomorphic to R, right? What about option 3?
It is not orthogonal.
Not orthogonal.
Okay, so close. If it was just a basis, then is it linearly independent? That we need to check.
Yeah, it is linearly independent.
Okay, so if this orthogonal word was not there, then the statement would have been true. But because it's given it's orthogonal, it is not true, right? Yeah, one is not a linear scalar multiple of the other. So it is a linearly independent set. So do you agree that this option would have been true if orthogonal was not there?
Yeah.
Yes.
Yeah, okay.
Ma'am?
Yes.
Hello, ma'am. Option 2.
Ma'am.
Why option 2 is wrong?
Because it is an orthogonal basis. No, here it's given it is not. For the same reasoning as in option 1.
Orthogonal means dot product is 0. So here dot product is not 0.
No, there is no second vector at all, no? Then how will you check orthogonal? If you have just one vector, it's vacuously orthogonal, right? Vacuously. There is nothing to check at all, so it is orthogonal.
So, ma'am, always when singleton set is given, so if it is asking orthogonal basis, so it is orthogonal because it is linearly independent.
Yeah.
But ma'am, in previously we see that always all linearly independent set is not on orthogonal basis. So here I am confused.
No, see, every linearly independent set need not be orthogonal. For that we saw examples, right?
Yes.
Something like this. Two vectors which are at an angle, certain angle other than 90 degrees. Okay, fine. So, but here we have only one vector. So only if there are two vectors, you can talk about angle between them, right?
Yes.
So if you just have one vector, then you assume that means the set is said to be orthogonal. It does not have a second vector with which you can check an angle at all. So it is orthogonal. Vacuously orthogonal means there is nothing to check with.
Okay.
What is the definition of an orthogonal set? Two non-zero vectors. It starts with two non-zero vectors. The second vector itself is not there. So you assume means it is vacuously true in the sense that this portion of the statement is missing. This is not at all possible. So you assume that the following statement is true. Whatever is happening after that is true. That's called vacuously true.
Okay.
Yeah. So there are no two vectors. That portion itself is not there. So you assume it is true in the sense that it is orthogonal.
Ma'am?
Yeah.
Ma'am,
Ma'am, in option 1, the transformation is not defined. They have not defined the transformation. So how can we say it is definitely isomorphic?
Yeah, so there is no transformation given, but to show that two vector spaces are isomorphic, it is enough if I define an isomorphism between them, right? A map which is 1-to-1 and onto, correct?
Yes, ma'am.
I am defining the isomorphism. I am defining what is T of x, y, z. And to define this isomorphism, it is enough if I define it on the basis, right? Once I know it on the basis, I know it on the entire space, right?
Yes, ma'am.
Yeah. So I'm defining that like this. T of 2, 1, 1. The first basis vector is going to the vector 1, 0. And the second basis vector is going to 1, 1.
But it can go to maybe 2, 4 and some other
Yeah,
thing.
fine.
Why 1, 0?
So suppose it goes to 2, 0. Suppose this goes to 2, 0.
2, 0.
Then what is the rank of this transformation?
1.
Rank of the transformation is 1. You agree, right? Because the range is one dimensional, right?
Yes, yes, ma'am.
But I want the rank to be 2, right? Because I want an isomorphism. So I am defining it like this, 1, 1. Now, do you agree the rank is 2?
Yes, now the rank is 2.
A basis going to another basis. This is a basis of R2, right?
Yes, ma'am.
Yeah. So now this linear transformation, yes, sir, 1 second. This linear transformation is both 1-to-1 and onto. Because the rank of this linear transformation is 2, nullity has to be 0.
0.
You can define anything. You'll put any other 1, 2, 3, 4.
Ma'am, is this true? Ma'am, is this true? If I have a basis for any subset and I transform it, then the basis for the basis of that transformation will also be linearly independent. Will be a basis.
It will be a basis for the range. That's what I've written here. V1, V2 is a basis for domain, implies TV1, TV2 is a basis for the range.
Range. So it
Here
will always
range
be.
Is R2.
Yes, ma'am. Okay.
This is always.
Then it is always be isomorphic. Then it will always be isomorphic. Yes.
So V is always isomorphic to T of V. Agreed?
Yes, ma'am.
Yeah, this is the range, not the codomain. Yes, sir. You were asking some question.
This is Shiva here. I was asking this question. Is there a way to find out all the transformations by looking at the base vector? Or so we know the base of R vector R2 will be either 1001 or 0111, or these are the three possible combinations, right? So is there a way to recognize all the possible transformations? You say, is there a shortcut basically? When
No. What are the three combinations you're talking about?
So let's say for the vector space R2, we can have the basis as 0, 1, 0, 1, 1, 1. Okay.
No, is this the basis for R2? This one?
Yes, possible. Yes, it is one of the possible bases.
Yeah, there are infinitely many bases, not just 3 as you said.
Yeah, no. There are infinitely possible. Is there a way to easily identify a possible base? It's like, is there any shortcut or something like that?
No, you see, the dimension of R2 is 2. So you just need to take 2 vectors which are not lying on the same line.
Same
plane,
line. That's it. Okay.
Yeah.
Okay.
Okay, I take back this statement that I made here. So I said V is isomorphic to TV. That's not what we should be talking about actually, because T is defined earlier there. So just ignore that statement. So any two vector spaces of the same dimension are isomorphic. Okay. Option 4. Is this an orthogonal basis for R3? How do we check that?
To inner product.
You just have to check whether it is orthogonal, right?
0.
Because it has 3 elements. If it is orthogonal, it will be linearly independent and hence it will be a basis, right?
No, it is not.
Okay, it is not, then fine.
It is not.
-1. This and this is not perpendicular.
Yes, ma'am. Compatible.
Yes.
Okay. Option 5. This is an orthonormal basis for R3. Yeah, that you can check. I guess it will be. Because you just need to check whether the set is orthonormal. That is, they are perpendicular, orthogonal to each other, and the norms are.
And the norm is 1.
See, option 1 is orthogonal. We have already determined. So this is orthonormal.
Okay, you need to check whether this vector is
Yes.
orthogonal to these two. Okay, fine. Yeah, it is. So it is an orthonormal basis for R3. Okay.
But denominator not the same.
Huh?
Denominator not same for every.
No, why should it be the same? You divide every vector by its norm, no? 2, 1, 1. What is the norm of 2, 1? Yeah.
Yes.
So the norm of this vector will be 1.
1. It is true.
Yeah. So is this concept of orthogonal basis, orthonormal basis clear?
Yes, ma'am. In option 2, there is an orthogonal basis, not here, then it is isomorphic to R.
Yeah. The same like how we did for option 1, you can do for option 2. Instead of R2 in option 1, you have R in option 2. And the dimension of the vector space spanned by this vector will be 1, right?
Yeah.
This not was not there, then it would have been isomorphic. Means option would have been right.
How the dimension will be 1 is in option 2.
Option 2, what is span of this set? Means what is the dimension of span of this?
Alpha times this vector.
No, what is the dimension? If this was W, what is the dimension?
Continuity.
2t.
Just one vector, no? So the dimension is 1.
1. Yeah.
Okay. So similarly for option 1, dimension is 2.
The span of these two elements is going to be 2-dimensional, no? Because they are linearly independent.
Yes. Correct.
What is the span of this vector? What is the span of this vector space?
It will be 1.
Yeah, because it's linearly independent set. Span means this can also be observed. So it's just equal to span of this vector.
That's correct.
Yeah, someone else had a doubt, right?
Yes, ma'am.
Yeah.
To have option 1 is correct and 3 is incorrect.
Is it clear why option 1 is correct?
Yes.
With all that we did. In
Yes.
B also you can do the same thing and get it as isomorphic to R, but there is a word not here, no? That's why it is.
No, 3. Option 3.
Option 3. Okay. This is not orthogonal.
Okay. But it is given is an orthogonal basis. That's true.
Yeah. If this orthogonal was not there, it would have been true. By the same logic as option 1. Because it's given as orthogonal, it is not true. Okay. Okay. Next is the concept of projection. What is projection? Suppose I have two vectors. If I want to project one vector on the other, what am I actually doing? What does projection mean? Suppose this is O, this is A, this is B. Suppose this is A vector and this is B vector. Suppose I want to project the vector A on B, what will I do?
Normal.
We take perpendicular from
shadow.
Yeah. And then you try to find this vector, right? Whatever is this vector, that is the projection of the A vector on B vector, right? So how will I get this vector? What is this vector? Now you told this is perpendicular, so you can talk about, you have a right angle. So this is A cos theta, right? If this is theta. Not A, the magnitude of A.
Magnitude of A.
Yeah. So the projection of the vector A along the direction of B vector is nothing but mod A cos theta. This is the length and the direction is B vector, right? Along the direction of B vector. Agree?
Yeah.
So this is nothing but A dot B by mod B. Agreed? Because I know that cos theta is equal to A dot B by mod A mod B. Agreed?
Yes, ma'am.
Thanks.
Norm A and norm B.
This is using dot product, no? So I'm talking about two vectors in R2 and all that. So it's all dot product. Instead of norm, yeah, it is the norm actually. The norm using dot product is nothing but modulus, no? Modulus of that vector, magnitude.
Yes.
Yeah. So the same concept we can generalize and write it in terms of inner products. So it's going to be inner product A comma B times B by, what is norm B?
B
inner product B comma B.
Square root of inner
under
product.
root of inner product.
Square
Yes,
root of.
So this is the concept of projection in inner product spaces. Same, this is what we see geometrically. The same concept has been extended to inner product. That's it. So the projection of one vector onto another vector is take inner product of those two vectors, divide by, and then basically you can write it like this: inner product of A comma B with the unit vector in the direction of B, right? This is a unit vector, right?
Yes.
Yeah.
It is providing direction.
Yeah. This unit vector is just giving the direction. And the magnitude is going to be the inner product of A and B.
Ma'am?
Yeah.
Ma'am, I did not understand in the formula of projection of A upon B, why we multiplied by B vector?
Because projection means after projecting, I am looking at this vector, right? This vector has a magnitude of mod A cos theta. And the direction is along the direction of B vector, right? Once you project, I want it in the direction of B vector, right?
Okay. Yes, ma'am. Magnitude of that and direction of this.
Direction is, yeah. So is the projection concept clear?
When we say unit vector, how would it be? Can for example, I'm thinking we can think of an example for basis, for example, 1 0 or 0 1. So, but when we talk of a unit vector, numerically, what can be one example?
Yeah. So you have a vector in R2. You want to find the unit vector in that direction, right?
Yes, ma'am.
So what you do is you just take the unit circle and then you find the point where the vector intersects the unit circle. That is your unit vector, geometrically. Okay. What is the distance of any point on the unit circle from the origin?
Distance of any point will be unit distance.
1. Yeah. That is what I'm doing. I'm taking any vector and then intersecting it with the unit circle. I will get a unit vector. A vector whose length is 1 along the direction of the vector that you wanted.
So 1 1 can be a unit vector?
No. 1 0 is a unit vector because it lies on the circle. 1 1 does not lie on the circle. Because 1 squared plus 1 squared. No, 1 squared plus 1 squared is 2, no?
Okay, yeah.
But what lies on the unit circle along this direction? 1 by root 2, comma 1 by root 2.
1 by root 2, okay, ma'am. Thanks.
1 by root 2 squared plus 1 by root 2 squared. How did I get this 1 by root 2, 1 by root 2?
So that the sum is, the norm is 1.
Yeah, but how did I think of this number?
If I had to do, I would just think that just take halves and square roots so that the sum comes out to be 1 because it's
No. Okay, then what about this vector? How will you check this vector's point of intersection with the circle?
We'll divide them by the norm respective.
Yeah.
Okay.
So V is any vector. V by norm V is a unit vector. So you just divide by the norm.
Yes.
Okay.
And this vector will intersect the unit circle.
Okay, so 2 3 is not a unit vector, but 2 by
2 squared plus 3 squared, whatever that
3
is.
squared.
5 4 plus 9 6 plus 4. Okay. Okay, so it is okay. Thanks.
Yeah. But now if I'm asking about what is the norm of this vector with respect to some other inner product, you have to use that inner product to calculate the norm.
If the formula changes, not the dot product.
Yeah.
Okay,
yeah.
Yep. Okay. Thanks.
Okay. So yeah. Okay. What happens when I apply projection twice? So I have already projected the vector. I want to know what happens to projection squared or projection of A vector in the direction of B vector. What happens now?
It will be square.
No, geometrically what happens?
Distance will be increased.
It is same vector, madam.
It is same, ma'am. There is no difference.
Yeah.
Projection of A.
It is already in the direction of B vector. Where will I project after that? Means a vector in the direction of B vector, if you project, it's going to be the same vector, right?
Yes, ma'am.
Yeah. So if you want to project the C vector, suppose this is C vector and this is B vector. If I want to project C vector in the direction of B vector, it is already in the direction of B vector. So there's nothing to project, right?
Yes.
Yeah. So projection, whatever projection you do, it satisfies this property that P squared is equal to P. So
Is
the
it
projection.
P to the power? Sorry. Is it P to the power N is equal to P? Any
No. P squared. P squared is P.
And if you again square it?
P cube will be P squared times P. P squared is P. So that's going to be P squared P. It's going to be the same. It will remain the same because once you have projected, it's not going to change direction after that, right?
Okay.
Yeah. So P power n is going to be P. But what is stronger is P squared itself is P, right? If P squared is P, then P power n is also going to be P. Right? Yeah. So yeah, let's look at projection as a function. So you have a function projection, or let's call it P. You have what you do, you here we projected a vector along another vector. But what if I want to project a vector on a subspace? So suppose I have R3 and I have a plane, which is a subspace. And then I have some vector here. If I want to project it onto this plane, what should I do?
You have to take a point in that plane.
XY.
Project it.
You need to find the point in the plane which is at the shortest distance to this vector, right? That's what perpendicular means.
Perpendicular.
Yeah.
Yes.
So a point in the plane is going to look, if it is on the plane, then it is going to have, the basis is going to have two vectors, right?
Yes.
Yeah. And then you want this vector to be perpendicular to both those vectors, right? Only then it's going to be perpendicular to the plane.
Yes.
Means you want to find the perpendicular distance, which means that. So in that case, what you do is it's always easy to deal with an orthonormal basis. So you take an orthonormal basis for the plane. Can you find an orthonormal basis for the plane always?
Yes, ma'am.
If
By
you have
dividing
orthogonal
it by
base,
the norm.
yes.
By dividing it by the norm.
No, but if the set is not orthogonal, then?
If it is orthogonal.
For a plane, we can take an orthogonal.
No, if I have this as the basis.
Yes, ma'am.
From here, how will I get an orthonormal basis? This is not orthogonal, right?
Yes, ma'am.
Yes, ma'am.
Yeah, for this you will use the Gram-Schmidt process, which we will see next. So for any vector space, you can always find an orthonormal basis using the Gram-Schmidt process. Okay, so now let us assume we have an orthonormal basis for the plane. Then you just need to do that inner product stuff, right? What we did for one vector. Yeah. What we did here for one vector, I have to do for both the vectors and then do some addition and all that, right?
By both vectors, do you mean the basis? Both the basis vectors?
Yeah.
Okay.
If I want a plane, then it will be two basis vectors.
So we have to make the point be perpendicular to both of these.
Yeah, both of the basis vectors.
Okay, then it will be perpendicular on the plane.
Yeah. Because that is how I get this perpendicular distance, right?
Okay.
Yeah. So that's what projection can be treated as a function from any point in the vector space to the subspace where you want to project it to. Okay. You're projecting it onto some subspace. That is your range, right? The output is going to be on the plane, right?
Yes.
And the input is you take any vector. You take any vector and you want to project. There is no condition on which vector you take, right? So the projection map can be seen as a function from the vector space to the subspace where you want to project. And what is the operation? Means what is the function? What is the definition of the function? What is P of V?
But here
projection
V is
V. Go
but
ahead.
here V is just one vector, not the entire vector space. We are taking.
Yeah. Okay, fine. Okay, let's come back to this. So how will you find the projection? Is by using this formula. So first you find an orthonormal basis for W. And then projection is going to be, suppose I have two vectors, v1, v2, means W is two-dimensional. Then the projection is going to be v comma v1 plus v comma v2. That's all. Oh, I missed the direction. V comma v1 v1 plus v comma v2 v2.
Ma'am, B is not there.
What is not there? No, v1 v2 is the basis. This.
So, yes, beyond B2 is basis. So norm, how norm beyond B dot B comma B come?
V is the vector that you want to project. Okay, let's get back here. So A is the vector you want to project.
Yes.
And in the direction of B vector. So can I take span of B as a one-dimensional space?
Yes.
Okay. So what am I doing in this case? I'm projecting it by using this formula. A with B and
Yes.
B norm B. B by norm B.
Norm. Yes.
Yeah. So
Yes.
what happens when you have more than two vectors? So there is a little bit of complication involved. So we assume that it is an orthonormal basis. If it is orthonormal basis, then norm B is going to be 1, right?
Yes,
orthonormal means it's all unit vectors.
Yes, ma'am.
So suppose you have an orthonormal basis, V1, V2. Then same thing. You do the same thing here. Instead of A, I am going to project the vector V. So V with V1 in the direction of V1 plus V with V2 in the direction of V2. That's all. That is projection.
Again, ma'am, what you saying?
So this is just a formula of how the projection works in subspace where you have more than one, means dimension of the subspace is more than one. Then what you do? When it is one dimensional, we see that projection of one vector on the other vector. You know how to get the formula, right?
Yes.
This is clear, right? So
yes.
I can see this as a vector here, A vector, being projected on the subspace whose span is this B vector. Means it is span of B vector. This can be treated as a subspace, right?
Yes, ma'am.
Yeah. Okay. Here I have drawn it as physical vectors, but I'm just telling it can be treated as.
I'm confused when many vectors projected.
So now this is one line. What happens if I want to project it on a plane? So if I want to project it on a plane, it's going to be more than one dimensional, right? Means
yes, ma'am.
plane is two dimensional, right? So in that case, I'll have two vectors in the basis. What I'm doing is I'm choosing an orthonormal basis for the vector space. ON basis, ONB.
Excuse me, ma'am.
Yeah.
If that vector projection on that plane will be in two position like that, is it correct, ma'am?
No. So here I have this vector. I'm going to project it here. So it's going to be a vector here. So if I remove all these lines, it's going to be some vector on the plane. It's going to lie on the plane. That's what projection is, right? Like you take a sphere and then you cut it in the middle. Okay, you cut or you take a watermelon and then you cut it in the middle into two halves. Now if I want to project that topmost portion of the watermelon in the thing, or what happens if I just push the watermelon onto the table after cutting it into two halves? I get a circle, right? Like
semicircle.
Yes.
Means I will get a hemisphere first of all after I cut the watermelon into two, and then I'm just pushing it onto the table such that it becomes it lies completely on the table. It becomes a circle, right?
Yes.
Yeah, so that's what we are doing here basically. You have something in the 3D plane. I want to push it into a paper. What am I doing? I have a point in the tree. I am trying to push it onto this plane, say.
Yes.
So I am trying to calculate. I am trying to calculate the perpendicular distance of this point from the plane.
Okay.
And the foot of the perpendicular is going to lie on the plane, right? That is the point I'm looking for. Agreed?
Yes, ma'am. Okay, ma'am.
So projection is a distance.
No, projection means the output is a vector which lies on the plane.
Okay,
the foot
it's a
of the
vector on the.
perpendicular.
Okay, ma'am.
Yeah.
And ma'am, why do we say it's on a subspace always? So projection can always be on a subspace.
No, we are talking about the projection of a vector to a subspace. That's all. See, here we projected a vector onto another vector, no?
Yeah, ma'am. What I'm trying to ask is that can it go? Can a projection be from one vector space to another one which has bigger dimension than it, or it will always
No,
be
that's
smaller?
not projection, no? Like projection means you are pushing it down, no?
Okay,
Suppose you have a point. Suppose you have a point in R. You cannot project it to a point in R2, right? Like, what does it mean?
Okay, that's what I'm trying to understand.
You can do this. You have a point in R2. I project it to the x-axis. Means I just push it down to the x-axis. How do I get that projection? I just take the x-coordinate of that, right?
Yes.
That's one way of projecting. But what did we do here? We projected it here, like this. You take the perpendicular distance along the direction of the x-axis. Yeah.
Thanks.
So here, instead of that vector B, which can be treated as a basis vector for this line, here we have two vectors if it is a plane. And we want it to be orthonormal so that certain complicated calculations become simple. That's it.
And ma'am, is standard basis always orthonormal?
Yes, why not?
Okay,
they're all orthogonal and their norms are all one, right?
Yeah. So when we want to project a vector to a subspace and we want to select an orthonormal basis, we can always select a standard basis.
Yes, unless you are, but what is the subspace? It depends on that, no?
Yeah.
Standard. The standard ordered basis is an orthonormal basis for Rn, means
for an
for
XY
R2
plane.
or R3.
If we know the plane only, then we can do. But okay, if the plane is not XY plane, then it won't work. It will be on that plane. We have to select the orthonormal basis.
Yeah.
Okay.
Yeah.
Thanks.
So if we want to project any vector onto a subspace, first find an orthonormal basis for the subspace and then use this formula. That's all. So this is for two vectors in the basis. If you have n vectors, do the same thing for all the n vectors. That's all. Is it clear how to find the projection of a vector onto a subspace?
Yes, ma'am.
Yes.
Ma'am, I have a question.
Yes.
Ma'am, a vector can be projected onto a single vector. That means one-dimensional vector. And it can also be projected into a two-dimensional vector. I mean, a vector space, two-dimensional vector space. That is like a plane.
Like this, yeah.
And we can also project it in three-dimensional plane.
Yeah, if you have a vector in fourth dimension, you talk about projecting it in third dimension. Otherwise, it doesn't make sense to talk about projection. No, projection means you're pushing it to some lower dimension, right?
Lower dimension, okay.
Yeah.
Yes, that was my question. We will always push it to a lower dimension.
So one dimension to three dimension not possible.
No, then that's not projection. No, you're expanding it or doing something. No.
Okay,
you're
ma'am.
projecting.
Yes,
Okay, so now look at
sorry, last
yes.
point in that same dimension also not possible.
No, like then it's going to be the same vector. No, if I'm projecting R2 onto R2, why do I want to make any change? This point will remain this point. That's all.
If
right?
it is a specific plane in R2, I don't know, but yeah. Okay, it's same dimension.
Then it will be like transformation.
It will be like that isomorphism. No, that's
fine. Yeah, it looks like.
Yes.
Okay, yeah, thanks.
Okay, so now look at this map P from V to W, where P of any V, you take any vector, the output is the projection of that vector on the subspace W. Does this make sense? Does this look like a linear transformation?
Yes.
Okay, you take my word for it that this is a linear transformation. This is a linear transformation because if you project the sum of two vectors, that's going to be equal to the sum of the projection of those two vectors. Or if you project alpha times the vector, it's going to be alpha times the projection of the vector and all that stuff. Okay, so take my word for it that this is a linear transformation. Now my question is, what is the range of this linear transformation? What do you mean by range? What is the range of this linear transformation?
Output.
Yeah, set of all outputs. So what is the range?
One output.
No, set of all outputs. Set of all
possible
outputs
values in W.
So what is the range?
W.
W.
Yeah, do you agree that the range is W?
Yes.
Yeah.
Yes, madam.
Ma'am.
Yes.
In this projection, we have only one vector in V, or we have multiple vectors.
No. You have a vector space. You take every vector, and then you see the projection. Means you see the output of this map. The output is projection onto W.
And that watermelon example was good. So in that example, the output is a circle, not a point. So yeah. So, yeah. Okay. Thanks.
No, not circle. In fact, it's the disk. No, you cover all the portion in between also because you're projecting it on. Yeah.
2D. Okay. Yeah. Thanks.
Okay. Now, why is the output W? Why is the range W?
It is the whole subspace of projection
where we project.
What is the guarantee that every point in W has a pre-image?
It is on a lower dimension first.
Yes.
So
W is a
dimension.
subset of V. Means W is a subspace of V. So every point in W remains in W, right? So we know that every point in W has at least one pre-image. That is the point itself, right?
Yeah.
Did I talk too much? Yeah, I guess. Okay.
No.
So my question is, why is range of P W? One thing, it is not bigger than W because I'm projecting it onto W. Means I'm trying to push it into W. So the range cannot be bigger than W. Why should it be equal to W? Is because every point in W has at least one pre-image. And the point in W itself is a pre-image, right?
Yes.
Because W is the subset of the domain.
Ma'am, it is isomorphism also.
No, why is it isomorphism? If W is bigger, V is bigger dimension, then that's not going to be an isomorphism, right? Yeah.
Yes.
So the projection, yes. Is there a question? No. Okay. So the projection. Yes. Please go ahead.
No. Go ahead.
Okay, fine. So the projection of vectors in V to W is a linear transformation from V to V whose image is W. That's what. Like you can talk about V to V, but the range of this linear transformation is W. image range. Is it
Yes.
clear?
Yes.
Yes.
Or you can talk about P from V to W. This is an onto map, right?
Yes.
Yeah. So we have noticed certain things here. We have spoken about the projection being a linear transformation and P squared being P. P squared here means P composite P. For a linear transformation, if we talk about powers, it means composition, right?
Yes, ma'am.
P of P, yeah. So now that we have a linear transformation, we can associate a matrix to the linear transformation, right?
Ma'am, can you explain that remarks part, please?
Which one? Projection, this one.
Yeah.
Projection of V is independent of the chosen orthonormal basis. Okay. Yeah. Whatever orthonormal basis you choose, there are infinitely many orthonormal bases, right? Infinitely many bases, so infinitely many orthonormal bases. Irrespective of what basis you choose, the projection is always going to be unique. Means this point cannot get projected to some other point under some other basis. It will always get projected to the same point.
Yeah. Okay. Thanks.
Yeah. So whatever basis you take, the projection of this vector is going to be one fixed vector. It cannot be multiple vectors for each basis.
For each basis, yeah.
Okay. So now, we have a linear transformation. We can talk about the matrix of linear transformation. So that matrix will also satisfy this. P squared is equal to P. So if a matrix is given, how do you check whether it is, okay, you cannot tell, okay, how do you check whether it corresponds to a projection or not?
Matrix A square is equal to A.
If A squared is not equal to A, we know for sure it is not a projection.
Not a projection.
Yeah. Okay, so we have spoken a lot of theory. Is there any example? Yeah. Consider the vector space R3 with usual inner product. So this is a vector space with an inner product. So it is an inner product space. Which of the following vectors represents projection of this vector onto the subspace whose orthonormal basis is this? So a subspace is given. This is span of 1 by root 2, 0, 1 by root 2, minus 2 by 3, 1 by 3, 2 by 3. It is already an orthonormal basis, so no work to be done, right? Now, how will I check the projection? Projection of 2, 1, minus 2 onto W.
Norm of 2, 1, minus 2.
Inner product of 2, 1, minus 2 with 1 by root 2, 0, 1 by root 2
divided
times the vector.
Vector divided by norm.
No, it's already orthonormal. So the norm is 1. Plus the same vector, take inner product with the other one, other basis vector.
Basis. Minus 2 upon 3, comma 1 upon 3, comma 2 upon 3.
Times that vector, that's all.
Yeah.
So you just calculate
the first option. Yeah, first option.
So you just calculate that and then you will get whatever is the answer. That is the projection of this vector onto the subspace spanned by these two vectors. So suppose this was not orthonormal. Suppose it was this. Then you will convert it into an orthonormal basis and then apply the formula. You cannot apply the formula directly. You have to first divide by the norm and then apply the formula.
Yeah.
And if the inner product is something different, you have to do the norm and all with respect to that inner product.
Okay.
Yeah.
So if it is defined in the question, then we have to do by this, right? If inner product is defined in the, yeah.
Here it is given, it is the usual inner product. Suppose the inner product was something else, you will find the norm according to that. This inner product will be according to that. Everything will be based on what is given in the question.
Okay. Okay.
Yeah. What about this question? Consider the vector space with the usual inner product. For projections, mostly we will give this usual inner product because it is easy to visualize the spaces. If ABC is the projection of the vector obtained by projecting this vector onto this subspace, find the value of this. Okay. What should you do? What is W first of all?
W is
1 minus 1.
1 minus 1.
This is
0.
W, right?
1 minus 1, 0.
Okay, find a basis for W.
0 minus 1, 1. 0
no,
minus
1 minus 1,
1,
0 doesn't satisfy, right?
It satisfies.
Is it satisfied?
No.
0 minus 1, 1.
0.
0 minus 1, 1. This also doesn't satisfy. No, see, it should satisfy this. 1 plus 1 minus 1 plus
Okay,
0 is
first
not equal.
1, 1, 0. Yes. 1, 1, 0.
Here also it will be 1.
Yeah, 1, 1. Sorry.
So this is what? This is a. Is this orthogonal? This is a basis. Is it orthogonal?
Basis. 1, 0, 1, 1. No.
No.
So you have to find an orthogonal basis.
Yeah, by dividing its norm.
No. This is
first we have
you
to
can
put
divide
it.
by
Use
norm
some other
to get
methods.
So from here you use the Gram-Schmidt process to get an orthogonal basis. Yeah, you can also get an orthonormal basis.
Normal basis.
So we'll see that and then we'll come back to this problem. Okay, once you get an orthonormal basis, you know how to solve this problem, right?
Yeah.
You just do, suppose V1, V2 is the orthonormal basis, then you do 1, 0, 1 with V1 times V1 plus 1, 0, 1 with V2 times V2. Yeah. So this is what you have to ultimately do. So how do we get this orthonormal basis? That is using the Gram-Schmidt process.
Gram-Schmidt process.
Yeah. So this is just an algorithm. You just need to find out. It means you just need to remember the algorithm. You will get the basis. So the Gram-Schmidt process is used to get an orthogonal basis from any given basis. So once you have an orthogonal basis, you can find an orthonormal basis, right?
Yes, ma'am.
Just by dividing by the norm. So yeah, a slight modification yields an orthonormal basis. These steps mentioned here will directly give you an orthonormal basis. Means the construction is such that it is orthonormal. So suppose you are given a basis V1, V2, Vn. Be the given ordered basis. What we are going to get, the orthonormal basis is U1, U2, Un. So what you do is you take the first vector and then you just divide by its norm. You divide the first vector by its norm. So you'll get a unit vector, right?
Yes, ma'am.
Yes, ma'am.
That is going to be your first vector here. And then you take the second vector, V2 here. What you do is you do V2 minus projection of V2 in the direction of U1. U1 is what you just obtained, the unit vector. This is your W2 and U2 is W2 by norm W2. All this U1, U2, UN, the final step is just dividing by the norm. So the intermediate step that you have is you do V2 minus projection of V2 in the direction of U1. Is it clear what is happening?
Yes, ma'am. That is quite calculation is too much.
Yeah, the calculation is a lot, but yeah. What you do for V3 is take the third vector, means for U3. So you take the third vector V3 minus projection of V3 on U1 minus projection of V3 on U2. So this is basically projecting it on the plane spanned by U1, U2, right? You remember the previous thing that we did?
Yes, ma'am.
So you take the basis, orthonormal basis as U1, U2, and then you project the vector V3 on that, you're going to get this formula, right?
Yeah.
So in this way, what you do is at each stage, you try to construct a perpendicular vector so that you end up with an orthonormal basis. So if you're okay memorizing things like these, then it's okay. Otherwise, you just remember the projection concept. And you know how to, you know the projection formula, so you just have to apply. So maybe we'll do one problem for you to get familiarized. Yeah, what is it?
So, ma'am, our problem, you can solve this.
This one, right?
Yes, ma'am.
This has only 2 vectors. I think I've taken one with 4 vectors or 3 vectors. Yeah, we can do the, we'll do this one or we'll do that one. Anything is fine. Okay, so now this is the basis. What is the first step? What is W1?
Ma'am.
Is his voice breaking only for me or for everyone?
For me also.
For everyone.
For everyone.
Okay. So can you put it on chat? I'll read it from chat.
1 by root 2, 1 by root 2, 0. That's what you're asking now?
Yeah. Okay. So can you tell me once he puts the message on chat, I'll come back and see. Yeah. So the first step is you have V1, V2. I want to convert it into an orthonormal basis U1, U2. So W1 is equal to, okay, U1 is equal to W1 is V1 by norm V1. Sir, are you telling something? Okay. So this is 1 by root 2, 1 by root 2, 0. Okay. Next is W2. W2 is V2 minus projection of V2 on what?
U1.
U1.
Yeah. So this is V2 minus inner product V2 with U1, U1. So 0, 1, 1 minus inner product of 0, 1, 1 with U1. 1 by root 2, 0 times 1 by root 2, 1 by root 2, 0. So this is 0, 1 by root 2, 0. Minus 1 by root 2 times 1 by root 2, 1 by root 2, 0. So this is 0, 1, 1 minus 1 by 2, 1 by 2, 0. So this is minus 1 by 2, 1 by 2, 1. At this stage, you can see that you would have got an orthogonal set before normalizing. Can you see? 1 by root 2 minus 1 by 2, 1 by root 2, 1 by 2, 1 into 0. Yeah. So you've got an orthogonal set. To get it, to make it orthonormal, U2 is W2 divided by norm W. So whatever is the norm of this, 1 by 4 plus 1 by 4 plus 1. This is 4 by 4. So 4, 5, 6, 6 by 4, 2 by 3, or what, 3 by 2. So the norm is root of 2 by 3. 1 by norm is root of 2 by 3 times 1 by 2, 1 by 2, 1. To simplify, maybe we can multiply and divide by root 2. So that's root 6, 1 by root 6 minus 1, 1, 2. Am I correct? I guess.
No, 2
Yes,
root.
ma'am.
Shouldn't it be 1 by root 2?
I've taken that root 2 here.
Yes, is it correct?
In the previous step, where the first step when we did V2 minus the inner product of V2 U1, the inner product of V2 U1 came out to be 0, 1 by root 2, 0. But we took it as
1 by root 2, 0. Inner product is a number, no? 0 times 1 by root.
Plus we have to do. Yeah, sorry. Now I got it. Sorry.
Yeah. Plus 1 times 0. So this is the inner product.
That's why it's 1 by root 2. Thanks.
So now that we have an orthonormal basis, you can check the norm of this vector is 1, norm of this vector is 1, and they are orthogonal to each other. And then using this, you can find the projection. Is it clear?
Yes, ma'am.
Okay.
But this question, find the value of ABC. So what is ABC?
The projection. ABC is the projection of the vector obtained from projecting this vector onto this subspace. So now we have an orthonormal basis. Projection is using that formula, V with V1, V1. Okay, here I have to write it as U1, the orthonormal basis.
U2.
After you find the orthonormal basis, you take this for the vector 1, 0, 1, where U1 and U2 forms the orthonormal basis.
Yes. Yes, madam. Madam, I have a question here. When we are subtracting the projection of U1 on V2,
okay,
when you computed W2, we are subtracting the projection of U1 on V2. I am only getting a shorter form of the vector. Why would these two be actually normal? Because
okay. So what are you actually doing? You have two vectors. Okay, let's suppose we have two vectors and I'm applying the Gram-Schmidt process to make them perpendicular. Okay, so let's take, this is one vector, this is another vector. This is V1, V2.
Yeah.
First step that I do is I make V1 a unit vector. So I just divide it by its norm and then it becomes a unit vector.
Yes.
And then what I do in the next step is I have V2 here. So I take the projection of V2 on U1. So that's going to be here. This is the projection of V2 on U1.
Correct.
Now I want, okay, so I want to construct a vector which is perpendicular to this vector, right?
Yeah.
Yeah. So that's going to be something like this. Let's assume it's this. Okay.
Yeah.
So what is actually happening is now this is perpendicular to this, right? Because that's the definition of projection. The foot
This
of
is
the
where I have a, this is where I have a confusion. When we say projection, this projected vector is lying on the actual vector itself, correct?
On the vector on which I want to project, yes.
Correct. So it is V2, let's call V2 dash as the projection. V2 dash is lying on V1 in the same direction, only the magnitude is different.
Yes. It is the foot of the perpendicular from V2 to V1. That's all.
Sorry.
It is the foot of the perpendicular from V2 to V1. You drop a perpendicular from V2, and the foot of the perpendicular is the projection.
Correct. So when I say the projection, it is already lying along V1, right? Or U1. Yes. Yeah. So when I'm subtracting these two, I am only subtracting the magnitude, isn't it? The direction is already set in the direction of V1. Or this is where my confusion is.
No. V2 minus projection. This is lying on U1. This is in V2. This is V2. Yeah, I'll do this. Maybe you will understand now.
Yeah.
So what I do is I complete this parallelogram. Okay. So I have U1 here. Then I drop this perpendicular. So this is also going to be 90 degree. So I complete this parallelogram. Okay. Yeah. It's going to be a rectangle, right?
Okay.
So this is going to be V2 dash. That is projection of V2 dash is projection of
V2 on V1.
Yeah. And I want to find this, right?
Yeah.
Because this is my perpendicular vector.
Correct.
Yeah. And how am I going to get that? This is my V2. This is my V2 dash. So this is going to be V2 minus V2 dash, right? Triangle law.
V2 minus V2 dash. You mean?
Or you can take this only. Take this only. Why you complete the parallelogram? Okay, yeah, you need to complete because this is the vector. This is the vector I want to find out.
Yeah.
So this is going to be V2 minus V2 dash. Do you agree?
Because the directions are such or
No. The triangle law or parallelogram law of addition. This is V2.
Yeah.
This is V1.
Yeah.
This is say U1. So this is my projection. Okay.
Yes.
This is my V2 dash. And now
okay, okay, the vertical one being, if we call it x dash, V2 dash plus x dash is equal to V2. That's how we are going, is it?
Yeah, I want to find the vector which is perpendicular to this vector, right? To this vector.
So, yeah, perpendicular one, if we call it as x dash.
It's going to be along this line because it will be parallel to this line. This is my perpendicular angle. So the vector will be parallel here. To find out what this vector is, I'm just completing this parallelogram. This is V2. This is V2 dash. So this is V2 minus V2 dash.
Okay.
And V2 dash is nothing but projection of V2 on U1.
Yeah.
So this is easier to see because I've taken the axis as my vectors. Means V1 I've taken on the x-axis, so this looks nice. But here it's tilted. Means the two vectors can be anyway, right? So here it's tilted. That's it. The same picture tilted.
So in a manner of speaking, if I say W2 plus projection of V2 onto U1 is actually equal to V2.
Yeah.
Because of the,
so you can see that here, right? From the parallelogram law, the diagonal is V2.
Yeah.
That's going to be the sum of those two vectors.
Got it. Sorry, ma'am. Sorry. I cannot visualize this completely.
No problem at all. So now like this, at each stage, you're going to build a perpendicular vector at each stage, which is perpendicular to all the previous vectors, right?
Yeah.
The next stage is going to come out of the page, means it's going to be in 3D.
Yeah.
And this is going to be my plane of projection there.
Yeah.
Yeah. So is it clear what this Gram-Schmidt process is actually doing?
Yes, ma'am.
Yes, ma'am.
Yeah. Yes, ma'am. So you just have to apply this formula to keep getting the vectors. So do you want me to solve this problem or will you do it on your own?
We do it on.
Please solve it, ma'am. That way, right? If somebody else watches this video who has missed out on the class today, if watches it, they will be able to understand how that was solved finally.
Yeah. Okay. Oh, what? Oh, you want me to solve it? Is it?
Yes. That way, if somebody misses this thing, they'll be able to look at it.
Okay. So, is there a Stat 2 session after this? Or are you
yes,
people
madam. Yes, there is.
leaving? Okay, so maybe we'll do one thing. This is the last topic. Orthogonal transformation is the last topic. Maybe I'll just define an orthogonal transformation and the Stat 2 people can, and and then we'll do the problem. Okay. So, yeah, orthogonal transformation. Anyway, even if I'm rushing now, you can ask on Tuesday's session if you haven't understood. So, Shubham will be there on Tuesday. Okay, so what is an orthogonal transformation? What we have now seen is orthogonal vectors. So what is an orthogonal transformation? So an orthogonal transformation is nothing but a transformation which preserves inner product. Okay, so what is happening? V is an inner product space. T is a transformation from V to V. To define orthogonal transformation, we always consider the linear transformation is on the vector space, that is V to V. Then it is said to be orthogonal if it satisfies this condition. That's all. Inner product of TV with TW should be equal to inner product of V with W. So what is happening here?
Ma'am, in the same space.
V to V, not V to W.
It's
so
like
suppose you have R2 to R2. Suppose you have two vectors, say these two vectors. The transformation, suppose it's converting it into these two vectors. What this says is the angle between them is preserved, right? The inner product of TV, say this is UV, this is TU or TV, TU. So the inner product, what?
Angle is same.
Yeah, it's preserved. That's it. It does some transformation, but it does it in such a way that the angle between the output vectors is same as the angle between the input vectors. Yeah, we can talk about angles when it is R2, R3 and all that. But yeah, the generalization of this is in terms of inner product. The angle concept is put into abstract spaces as inner product. That's it.
It's like, ma'am, similarity.
Similarity. Okay. Yeah, in some sense, something is preserved. Yes. If that is the thing, then yes.
Madam, if we were to combine affine transformation and this one, is it going to be giving both translation and rotation?
No, like combine in what sense? Here we are talking only about linear transformation. So we want 0 to go to 0.
Yeah. So if I actually give a affine transformation to this, it will go somewhere else and also rotate. Is that the way it is to be actually seen?
No, it's not necessary that it should rotate. Okay, yeah, you can. Rotation is also an orthogonal transformation, but every orthogonal transformation need not be a rotation. Means the image that I have drawn here is a rotation.
But I've seen in some question in graded assignment, this tell us some rotation type.
Yeah, rotation is also an orthogonal transformation. Means just like how dot product is an inner product, rotation is an orthogonal transformation. Not every orthogonal transformation is a rotation. Yeah, so you can just keep this in mind. Inner product is preserved. Inner product of the output vectors is equal to inner product of the input vectors. If this happens, then it is an orthogonal transformation. And the matrix corresponding to an orthogonal transformation will satisfy this. A transpose is equal to A transpose A is equal to identity.
Madam, can you give an example of A transpose is equal to I from
Yeah,
program?
we have no. So you take, yeah, for this. Okay, now that you've asked this question, before doing this problem, what does it mean to say AA transpose is identity? First of all, what is AA transpose? In general, take A is any M cross N matrix. So what is A transpose?
N
cross
M.
A transpose is going to be M cross M. And A transpose A is going to be N cross N. So whatever be the order of A transpose and A transpose A is well defined product, right? And these two are going to be square matrices.
Square matrix, yeah.
Yeah. Okay, what is happening when you do A transpose? Or let's take A transpose A first, that's easier to see.
Aren't we doing the dot product again?
Yeah, dot product of what?
The same vector. Row vectors becomes column vectors.
Yes. Yeah. You're almost there. Which one? Row or column?
I mean, like if A it is a row vector,
Yeah,
automatically it becomes a transpose in the row column vector in the transpose. So I'm multiplying the vector with the vector on a dot product.
Yeah, which vector with which vector?
A into A. A
no,
dot
A is a matrix.
Norm A dot. Normal.
Okay. A has n columns, right?
Yeah.
So A transpose is going to have n rows. So let me write down the columns.
So A1 will be multiplied with A1, A2 will be multiplied with A2, right?
What is A1? That is the thing.
A1 is a row vector in this case.
No, columns, right?
Column. Okay, sorry, column vector. Yep.
So this is going to be A1 transpose, A2 transpose, and all that. So AIs are the columns of A. And what are you actually doing? A1 transpose will be the first row of A transpose. Okay. So what you do in this multiplication, you multiply the first row of A transpose with the first column of A, right? Entry wise. So what are you actually doing there?
A1 dot
product.
Yeah. You're doing the dot product of A1 with A1, right? And what is the next entry?
A2.
A2.
No, the first row with the second column.
A1, A2.
A1, A2. Like that, A1, AN.
AN.
And in the second row, it's starting with A2, A1, A2, 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 AN.
So it's like an identity matrix.
You'll get a square matrix.
If they're all orthogonal, otherwise no.
Exactly.
All are 0 except.
If it is orthogonal, if all these columns are orthogonal, then all these entries are going to be 0, right?
Yeah.
Except the diagonal entries, all the other entries are going to be 0. Except these entries, everything else is going to be 0 if the columns are orthogonal, right?
Yes.
And what happens to the diagonal entries?
It will be 1.
1.
If it is orthonormal, it will be 1.
Orthonormal, yeah.
So if this is the identity matrix, it means that the columns form an orthonormal set. And if the columns form an orthonormal set, this will be the identity matrix.
Ma'am, can I ask you? Yes, ma'am. Ma'am, in this question, in activity question, here is given identity matrix and not an identity, it is a diagonal matrix. And all the upper triangle is 0, 0. So it is also called a lower triangle or upper triangle also.
Yeah. Activity 8.2 question number 5, madam. Same concept. Can you?
Yeah,
Could you
we will
please
do that. One second. Before doing that, we'll just discuss what happens to A transpose, AA transpose. If AA transpose, what happens in AA transpose? With the same concept, what is happening there?
Then it is row vectors.
Yeah, you consider the rows of A here, right? The same concept for rows of A, right? Because AA transpose means the first row of A is multiplied with the first row of A again. First column of A transpose is the first row of A, right?
Yes, ma'am.
So here A transpose deals with rows of A transpose A deals with columns of A. So is this concept clear?
Yes,
that when you're talking about orthogonal matrices, you need to check that all the columns form an orthonormal set and all the rows form an orthonormal set.
Now, first column, like first column of A transpose multiply with first row of A.
No. How do you do matrix multiplication? First row of the first matrix is multiplied with first column.
First column of second matrix.
Yeah.
Yeah. So, but here we have taken first column, madam. Why A transpose into A?
No.
We are multiplying.
The first column. What is the first row of A transpose?
First row of A, first column.
First column of A, right?
First column of
A. So that's what I've written here. First column of A with first column of A.
Okay.
Right? Because the first column of A, first row of A transpose is the first column of A.
Yeah.
So this is in general for any M cross N. Now, suppose A is an N cross N matrix. It is a square matrix. What can you tell about this condition and this condition? If one is satisfied, is the other naturally satisfied?
Yes.
Yes.
Why?
It's only possible if they are not orthogonal.
If it is A transpose.
Okay, if this is satisfied, what is A transpose?
A transpose is IA inverse.
Inverse.
I mean, I hope that is what you're asking. Yeah.
A inverse.
A inverse I.
So can you see that if this is satisfied for a matrix, the inverse of the matrix is very easy to calculate, right?
Yes. Yes. All we need to do is
transpose. Yeah. So now, can I post multiply by A? Can I multiply A on the right side for both the matrices? These two are equal. So I do this.
So it got an identity matrix.
So you've got this, right?
Yeah.
This is only for square matrices, not for rectangular matrices, because there is no concept of inverse for rectangular matrices, right? So
yes, ma'am.
If one of this is satisfied, the other is satisfied only because it is a square matrix. If it is a rectangular matrix, this does not hold. You can even try examples where one of this is satisfied and the other is not satisfied.
Yes.
But is there an identity in a rectangular matrix, madam?
No. See, identity comes into picture only for A transpose and A transpose A.
And
These two are always
matrices,
square
correct?
matrices. These two are always square. Even
Okay,
if A is a rectangular matrix, these two are always square.
Yeah.
So yeah, you keep all these things in mind and try out examples where one of this is satisfied, the other is not satisfied. But if it is a square matrix, these two are equivalent. If one is satisfied, the other is always satisfied. So can I tell that if the columns of A form a orthonormal set, then the rows of A also form an orthonormal set if it is a square matrix?
Yes, ma'am.
Yes.
Yeah. Because A transpose is equal to identity is equivalent to telling that the rows are mutually orthonormal. So for a square matrix, to check if it is orthogonal, You have to check if the columns are orthonormal or rows are orthonormal. That's it, right?
Yeah.
What about the first option? Is it orthogonal matrix?
Yes, ma'am.
Check this column is orthogonal to this column or not, and are they unit vectors? That's all.
Yeah, they are.
So, what about the second one?
Yeah, it is also orthogonal.
Yeah. Third one?
Hello, ma'am.
Third one is not, I guess. Third one is not.
Yeah, clearly it's not divided by the norm, no?
Yeah.
Yeah. The last one? Just keep checking. Someone had called for in between. Yeah, there was someone with a doubt, no? What is it?
Yes, I can get for a question of a first option, but that is true.
So one thing you can do for fourth one is?
Fourth one is also correct. Yeah.
Okay. So the first one thing to check whether it is an orthogonal matrix, you can check whether A transpose is identity, A transpose A is identity, and all that. Okay, you can do that. But another way of checking, another way of checking, what did we see? If A transpose is identity, then A transpose A will also be identity because we are looking at square matrices.
Yeah.
And if A transpose is identity, it means that the rows of A form an orthonormal set. That's what we saw here. Yeah. And if A transpose A is identity, it means that the columns form an orthonormal set. So instead of doing this calculation, you can just take the first column, second column, and check whether it forms an orthonormal set. That's all.
So there also will be actually multiplying, isn't it, madam?
Yeah, but here it's just dot product, no? 1, 0, 0 minus 1. So this is simpler than doing this. Because you have to first write down what is A transpose and then multiply and all that, right?
Yeah.
Ma'am, sometimes columns are orthonormal, but rows are not orthonormal. So in that case, this is
no, that will not happen if it is square matrix. Because if it is square matrix, we have proved this. A transpose is identity if and only if A transpose A is identity.
Yeah, it always will be true.
The same problem I have. I am facing question number 5, activity 8.2, ma'am. Because that is also a square matrix, but columns are orthogonal, but I think rows are not.
No, not orthogonal. I'm talking about orthonormal.
Normals, okay. Orthonormal.
If columns may be orthogonal, but rows may not be orthogonal. What I'm talking is about orthonormal. That B matrix or something, right? That
B matrix. I am also not getting B matrix also properly in that.
So what is A here? Can you quickly tell me A? 2, 2, 7.
Here 2, 2, 7, 2. A coefficient matrix 2, 2, 2, 7. And 1. I'm not. 2 to 7, 2 to 1 minus 10.
3 minus 2.
3 minus 2. Yeah.
Okay. What is B? Let B be the matrix containing the column vectors of A, which are normalized by their respective norms as its columns. Okay. So what is B? How will you find out B?
Column vector of matrix A. What is meaning, madam? Column vector of matrix.
Normalized. Let a matrix B contain the column vectors of A, which are normalized by their respective norms as its columns. So the columns of B are columns of A after normalization. What is normalization?
Divide by norm.
Root 13.
You divide by the
Unit
norm.
vectors.
That's it.
And the unit vector.
You convert it into unit vectors, right? So that's going to be 2 by 4 plus 4 plus 9.
Root 13. Root 13.
Okay. 2 by root 13. 2 by root 13. 3 by root 13. And then 4, 4, 5, 8, 9, 3.
2.
2 by 3 minus 1 by 3. Oh, 1 by 3 minus 2 by 3. And then 49, 149 plus 4, 153. 7 by square root of 153 minus 10 by square root of 153. 2 by square root of 153.
And
Okay.
first column will have root 17, I think, as denominator.
Oh, 4 plus 4 plus 9. Yeah. 70. Okay. Now, what can you tell about the columns of B? They're all unit vectors, right? First of all, because we have divided by the norm.
Yes, yes, madam.
Okay. Are they orthogonal?
Yeah.
4 plus 2, 6,
Yes.
minus 6, 0. 14 minus 20 plus 6, 0.
Column wise it is orthogonal, but row wise it is not orthonormal. Row wise, madam.
Okay, row wise. 4 plus what? 2. 4 by 17 plus 2 by 9 minus 70 by 153. This will be 0. Here it is not 0. But once you divide by the norm, this is going to be 0.
Okay. After dividing norms, it is. Okay.
If rows are orthonormal, if and only if columns are orthonormal. This doesn't hold for orthogonal, only for orthonormal.
Okay, okay, madam. It is only for orthonormal. I am taking
so
for
here
orthogonal.
it will not hold. But here, after you divide by the norm, it will hold.
Yes. Now it is clear.
So is an orthogonal matrix clear? The concept of an orthogonal matrix?
Yes, ma'am.
Okay. What is an orthogonal transformation? How do you check it as an orthogonal transformation? So you have to go by the definition. So let's do this problem. Here we are given T1, T2, T3, T4. T1 and T2 are from R2 to R2. T3 and T4 are from R3 to R2. Okay, here you have the other one also. T from V to W is also given. Means a different inner products. Means different inner product spaces. So it's the same concept. TU comma TB. Okay, TB comma TW should be equal to V comma W. Yeah. So let's check T2 first. Is T2 an inner product? An orthogonal transformation?
No, ma'am.
Why isn't it? This should hold for all V and W.
Yeah, this should. Answer.
Okay, what will be the matrix of T2 with respect to the standard ordered basis, say? or is it transpose of this 1, 1, 2?
I think transpose.
Transpose, ma'am.
T of 1, 0 is 1, 2.
1.
Okay, 1, 2, 3 minus 2. Huh. So if this is corresponding to an orthogonal transformation, this matrix has to be orthogonal, right?
Yes, ma'am.
But it's not orthogonal, right?
No.
Yeah. Clearly, these are not unit vectors. There itself it ends. So you cannot take any random basis, okay? You have to take only orthonormal basis. That's why I took the easiest orthonormal basis, which is the standard ordered basis.
Ma'am, can we solve simply through taking inner product? Yeah. LHS, RHS
you just you want to show this does not hold for at least one pair of vectors v and w, right? Because if it holds for all, then it is an orthogonal transformation. So maybe you suggest some vectors
like T2, T1. Yeah.
1, 0, 1, 1. Okay, what is the inner product of these two vectors?
1 plus 2. 1.
What is T2 of 1, 0 with T2 of 1, 1? Inner product T2 of 1, 0 is 1, 2. T2 of 1, 1 is 4, 0.
Yeah. So 4.
Not equal, right?
Not equal.
Yeah.
So T1 and T2 are not orthogonal.
T2 is not an orthogonal transformation. Try T3.
It will also not be holding.
Vectors?
1 plus.
It is not even a square matrix.
No, even if it is not square matrix, yeah, we can talk about the inner products being equal. So that's not an issue.
Yeah.
But in this, if we have to
like
check
if you are
matrix,
taking 1, 0, 0 or 0, 1, 0, then inner product is coming 0. But
0, 1,
when we are
0.
making,
okay.
then inner product is coming 0, and then when we are taking transformation, then it is coming 1 upon root 3, I guess.
Okay.
Yeah.
Let's check. 1 plus 1 by root 2.
Comma 1 upon root 3.
1 by
1
root
upon
3.
root 3.
Okay. Comma 0, 1, 0. 0, 1. Right.
So it is coming 1 upon root 3. It is not equal to 0. So
yeah. So two orthogonal vectors going to two vectors which are not orthogonal. So this is not an orthogonal transformation.
Can this question be done by making a matrix out of this?
Okay, yeah, it can, but I'm not telling that because Sir has defined orthogonal matrices only for square matrices. There is a concept of rectangular matrices also, but let's not go to that.
Okay. Ma'am, T4 is also not orthogonal.
Okay, T4.
I have taken again
same
1
should
comma,
help, right?
Yeah. 1 comma 0 comma 0 and 0 1.
This is 0. T4 of 1 0 0 comma T4 of 0 1 0. This is
coming 2.
1 1 comma 1 1.
Yeah. It's 2.
So is it clear how to check whether a linear transformation is orthogonal or not? Okay, these are all not.
Yes,
T1 it is, so let's check T1. T1 is defined as x plus y by root 2 comma x minus y by root 2.
Yeah.
What is TV, TW? Okay, let's call V as x1, y1, W as x2, y2. So what is TV? Do you understand that this x comma y is because it belongs to R2?
Yes, ma'am. Yes, ma'am.
Yeah, not because it's an inner product or anything.
Yeah.
Because it belongs to R2. This is the domain of T1. So it has
T1.
the ordered pair x comma y.
Yeah.
Okay. So this is going to be x plus y by root 2. That is x plus y. The first coordinate of V plus the second coordinate of V by root 2, comma x minus
x1 y upon root 2
by root. Same for W. x2 plus y2 by root 2, comma
x2 minus y2 upon root 2.
Okay, then
yes, ma'am, it's coming.
I can take this 1 by root 2 from both outside. I'll take it as 1 by 2.
Yeah.
So this is x1 plus y1 into x2 plus y2 plus
half
x1 minus y1 into x2 minus y2.
Right. Yeah.
So this is half x1 x2 plus x1 y2 plus y1 x2 plus y1 y2 plus x1 x2 minus x1 y2 minus y1 x2 plus y1 y2 x1 y2. So this is x1 x2 plus y1 y2. This is nothing but inner product of x1 y1 comma x2 y2. So this is how you check whether it is an inner product or not. There's nothing special about V and W, so this is true for all V comma W in R2, so it works. So can you see that this, because of this minus sign only, some terms are getting cancelled, right?
Yeah.
So if everything was plus, then terms wouldn't have got cancelled. So having too much of plus like this is not going to work, right?
Yeah.
Same here.
Same, yeah.
There is a minus here, but again, you have x plus 3y, 2x minus 2y. So the coefficients are all going to be some kind of a different. Yeah, it's too much away from each other that you will have terms that get added up and they don't get subtracted because the numbers are all somewhat weird.
Yeah.
So that's like some kind of a intuition to tell you that it's not. So try for a counter example instead of trying for a proof.
Yeah.
This is how you check orthogonal transformations, whether it is orthogonal, not orthogonal. So is it clear to everyone?
Yes, madam. Yes.
Did someone say no?
Yes, madam. Okay.
Okay.
No, ma'am. No one said no.
Okay, fine. So maybe we will do this Gram-Schmidt process one problem and end the session. And yeah, we have covered the entire week 8. So
yes, ma'am.
On Tuesday,
after so many days, we have covered whole week in just one day.
In one session, yeah.
Yeah, one session, correct.
And that too just in 2.5 hours, not 4-5 hours.
And that too week 8. That's important.
Yeah.
That is why, ma'am, because mock test is coming after 2 days.
Yeah, but even otherwise we would have done, right? Like.
Yeah.
Everybody is study before.
No, but ma'am also covered all the topics.
The portal will be off tomorrow and the day after. So you should probably be studying from your notes. If you have registered for Python, right? You won't be able to access anything, any of the contents.
Nothing.
Yes.
Like not maths and stats.
Ma'am, if it is not Python, then is it okay?
I think you should be able to access. If you are not registered for Python, I think you should get the access. That's what I was told, but yeah.
Okay.
Ma'am, what is the reason behind it?
There's this OPP exam that's happening tomorrow. Online for the Python course people.
It's on Sunday.
Tomorrow and day after. Tomorrow.
Oh, for some students it may be tomorrow then.
Okay.
I don't know. For me it's on Sunday.
Okay, fine. But I think you will not be able to access on both days, right? Even if you don't have exam tomorrow.
Have to check.
Yeah, probably.
Yeah, that's what I think it is.
Yeah.
Well, for me, everything is pending, so that will be a huge impact.
But maybe you can download all the live session PDFs and all that and keep. Whatever is downloaded, maybe you can do all that and keep so that you can work on it.
Okay, ma'am. Yeah. Thank you so much for telling.
Anyway, Monday, Tuesday.
Even the other videos also available on YouTube, right? Even the lecture videos are available on
YouTube.
Yeah.
You can find it on YouTube, so that's not an issue.
Just copy the link, keep a copy of the links ready. So
yeah, maybe you can keep the playlist link bookmarked so that you can access. Okay, let's quickly do this problem then. So we have an ordered basis. V1 is 1, 1, minus 1. V2 is 1, 1, 0. V3 is 1, 0, 0. Okay. What is the first step?
W1.
W1 is V1 itself. So yeah, or you can take it as U1, anything. U1 will be norm of
W1.
1 by 3, this. Okay. W2 is
110.
V2 minus projection of
V2 on U1.
Yeah. So V2 minus inner product V2 with U1. So 1, 1, 0 minus inner product of V2 with U1. 1, 1, 2, 2 by root 3 times 1 by root 3, 1, 1 minus 1. Right?
Yes, ma'am.
So this is 1, 1, 0 minus 2 by 3, 2 by 3 minus 2 by 3. So this is 1 minus 2 by 3, 1 by 3, 1 minus 2 by 3, 1 by 3 plus 2 by 3. Okay. What is U2?
U2
1 by square root of 1 by 9 plus 1 by 9 plus 4 by 9 times 1 by 3, 1 by 3, 2 by 3.
2 by 3.
9 goes to the top, 3, all the 3's get cancelled, 1 by root 6. Gram-Schmidt process is just calculation. You shouldn't make a mistake. That's it. Because if you make a mistake at one stage, every subsequent stage is going to be wrong, right?
Yeah.
Yes, ma'am.
So you have to be very careful. W3 is V3 minus projection of V3 on U1 minus projection of V3 on U2 on both the vectors. Means you want V3 means W3 to be perpendicular to the plane that is generated by U1 and U2. That is V3 minus inner product V3 with U1 U1 I'm not dividing by norm u1 and all because they are unit vectors. That is why we want to convert it into orthonormal basis. You can do for orthogonal basis also. Everywhere you'll have to divide by norm. That's all. U2. So V3 is 1, 0, 0. V3 with U1, 1 by root 3 times 1 by root 3, 1, 1 minus 1. V3 with U2, that's 1 by root 6, 1 by root 6, 1, 1, 2. So that's 1, 0, 0 minus 1 by 3, 1 by 3 minus 1 by 3 minus 1 by 6, 1 by 6, 1 by 3. So this is 1 minus 1 by 3 minus 1 by 6. 1 by 3 plus 1 by 6. 6 plus 3, 9 by 3 into 6, 3, 2. 1 by 2. 1 by 2, 1 minus 1 by 2, 1 by 2. 0 minus 1 by 3 minus 1 by 6. So that's minus 1 by 2. 0 plus 1 by 3 minus 1 by 2. Is this correct? Okay. So U3 will be 1 by square root of 1 by 4 plus 1 by 4 plus 0 times 1 by 2 minus 1 by 2, 0. 1 by root 2, 2, 1 by root 2 minus 1 by root 2, 0. Or okay, we can write it as 1 by root 2 times 1 minus 1, 0. So to check whether you've got the right answer, all that you need to do is write down U1, U2, U3 and check whether that forms an orthonormal set. If yes, then your answer is right. One, 1 minus 1. 1 by root 6. 1, 1. 1 by root 2, 1 minus 1. 1, 2 minus 2, 0. 1 minus 1, 0, right? 1 minus 1, 0, right? Yes, this is an orthonormal basis. So you can just quickly check whether they are mutually orthogonal, and already we have divided by their norms, so that's fine. Is it clear?
Yes, ma'am.
Okay. So please attend the mock, because it's okay if you get low marks because you still have a lot of time to study for the quiz. Only if you attempt the mock, you will know where you stand. Only then you will know whether you're able to answer questions, because quiz 2 paper will be similar to the mock paper. Same as quiz 1. Just like how mock 1 was similar to quiz 1, mock 2 will be similar to quiz 2. So if you attempt, you will know where you stand, what is it that you're lagging behind in and all that, and we'll have 2 revision sessions so you can get your doubts clarified there.
When is the mock?
Monday, Tuesday.
Monday, Tuesday. Okay.
Yeah.
Fine.
It'll be open on both days anyway. It will be on the portal even after that, but still, if you want to attempt it live.
So, ma'am,
it won't be a timed mock, so you'll have all the time to attempt it.
Okay, sure. That is better, because on Monday and Tuesday we have offices, or most of the people have offices. I suspect our students have other things to do. So timed mock is difficult.
Ma'am, even I am not giving the OPP exam, so we cannot open the portal. We also cannot open the.
I think she's
Have you
not
registered
sure.
for Python?
No, ma'am.
I don't know. Actually, last time I remember someone telling on discourse, even those who are not registered for Python couldn't open. But the team told me that's not the case. Only if they have registered for Python, they will not be able to open. That's what the team
Yes,
had told
ma'am.
me. Okay.
Yes, ma'am. That is the case.
Okay, then good.
Which is informed.
Okay. So maybe you should Tuesday fully. You can ask all doubts and finish week 8.
So one more session will be for week 8, right?
Yeah. Tomorrow there won't be a live session.
Yeah.
Instead, Tuesday, the usual time slot, 8 o'clock. There'll be a session on Tuesday. Okay. Then maybe we'll close.
Thank you very much, ma'am.
Thank you.
Thank you.
Thank you, ma'am.
Yeah.
Ma'am, just one understanding I want to check. Can I?
Yeah. Yeah, sure.
Yeah, about that projection function. What I have understood is like we are splitting W into unit vector in all possible direction and taking the projection of V along all the possible direction of W, and then adding that because that is the net thing, right?
Projection or Gram-Schmidt process?
No, ma'am, that projection thing.
Okay. Yeah. You are finding an orthonormal basis for W. That is a basis vectors which are perpendicular to each other and unit vectors. And then you're trying to do the projection. There is nothing special about orthonormal basis. Means it's only making the calculation, the formula so much simpler. You can do it even with a normal basis. But if you do it with a normal basis, it's going to look like a very complicated thing. So when you do this, it's just going to like the foot of the perpendicular. We are interested in some kind of a perpendicular. So orthonormal basis helps easily.
Yeah, so I just wanted to ask that can we say that we are splitting W into unit vector in all possible direction and then taking the projection of V along all the possible direction of W and then adding that because of that net thing?
Not all possible directions, along the directions of the basis vectors. Means just one or two directions, whatever is the dimension of W, along those directions.
That is the possible.
Means if it's two-dimensional, in some sense you're trying to make it look like R2 and then you're projecting.
Correct.
It's like
yeah.
R2 with the axis as the basis, like so that they are perpendicular to each other.
Yes, ma'am. Yeah. Okay, ma'am. Thank you.
Okay, thank you.
Thank you, ma'am. Good night, ma'am.
Good night.
Good night. Thank you.
Thank you.